Before the session began, Dr. Key reviewed the mixing process covered in the previous class, taking the solvent NPM used in PBS slurry formulation as an entry point. He introduced the broader topic of solvent selection for different materials, a subject of common interest to the audience. In slurry preparation, both formulation and mixing share the same fundamental requirements: drying, moisture control, dispersion, and system stability. When graphite is placed in water, it generally floats on the surface because its surface is hydrophobic. To address this issue, CMC is introduced into the anode slurry formulation. The role of CMC is to enable effective wetting at the graphite-water interface, thereby facilitating proper dispersion. In addition, it is worth noting that graphite itself comes in many different forms, including spherical graphite, flake graphite, and secondary agglomerated particles, among others. Primary particles and secondary particles exhibit clear differences. Specifically, secondary particles are more difficult to achieve complete wetting across the entire surface. Therefore, conventional anode slurry mixing processes are typically suitable for primary graphite particles. However, secondary graphite particles require a different approach, namely kneading mixing, which is also widely used in industry today. This method essentially corresponds to high viscosity mixing, and the principle is similar to kneading dough, adding a small amount of water and continuously kneading to ensure sufficient surface wetting of the material. These points illustrate two key takeaways. 1. The use of CMC is necessary, and second, the mixing method must be selected according to the material characteristics. The comparison shown in this image clearly demonstrates the impact of CMC on slurry behavior. After CMC is added, the slurry exhibits improved flowability and the particles become effectively dispersed, resulting in a dramatic difference in the coating outcome. It is important to highlight that battery-grade binders are almost entirely imported and are subject to stringent performance requirements. One cannot simply use any material labeled as CMC. Although many variants of CMC exist, only specific grades formulated for battery applications can deliver the required performance. Therefore, CMC plays a critical and widely adopted role in anode slurry mixing. Next, we look at SBR, which represents another major component of the slurry and serves as a binder. Here, I use styrene butadiene rubber as an example because it is the most commonly used system. Of course, other binders such as PAN, PA, PI, and sodium alginate have also been introduced in recent years. Even within SBR itself, the monomer composition can be tailored, for instance, by incorporating new monomers or modifying the functional groups. SBR is typically supplied in the form of an emulsion, as shown in the glass bottle above. Once dried, it becomes a rubber-like solid. In SEM images, the presence of SBR between the active material particles and the current collector can be clearly observed, illustrating how it provides the mechanical adhesion required for electrode integrity.